how to represent molecules and species and functional groups and so on in RMG. This is important for making your very first input file. You need to tell RMG which species you want to include. Also for interpreting the results, knowing what species it's made, you need to turn its representations back into molecules you understand. Debugging is where it's especially helpful to understand the language of how RMG describes molecules. It'll say, if you start delving into why did this thing go wrong, you say, show me the molecule, and it will spit out a description that you need to understand. How to represent species in an input file. Our current input file format, you'll see things like this where it says species. Oh, sorry. It gives you we give it the label, we tell it if it's reactive, the default is true, and then we give it the structure, which you can give it in various ways. We can give it with a smile string. I'll talk more about those in a slide or two. An adjacency list, and also it can translate from inchy strings and smart strings. So there's a few different routes you can get it in there. Smiles is convenient. It's much shorter. You can describe methane with just a single character. Just a capital C is methane. But adjacency list is the more canonical, is how RMG thinks and describes things. So I'll talk through what an adjacency list means. It's a list of what is adjacent to what, basically, and it's the most detailed description for input and output to RMG. But there are various options. So a little bit about SMILE strings. It stands for Simplified Molecular Input Line Entry System. And so it's a very concise notation widely used in cheminformatics to describe molecules. For hydrocarbons, you just give the heavy atoms, and the hydrogens are all assumed or implicit. So if you just say capital C, it represents methane, and the 4 hydrogens are implicit. Ethane is CC. If you want to make it a double bond, you put an equal sign in. A triple bond would be a hash symbol, like a hashtag. You can do ethanol with CCO because the hydrogens are implicit again, so the hydrogen on that oxygen is assumed to be there. One gotcha is therefore that an O is not an O atom, it's water. Now, when you're inputting things in the, we'll get onto the RMG website in a second, but it kind of has an order of, it tries to interpret it first as a smiles and then falls back to other options. Anyway, just first caveat, warning is check that what you got is what you intended, because sometimes there are surprises. So I always do a round trip. If I think I've entered the right thing, I get it to like show me what I just entered to just double check. Rings you do in a smile string with these numbers. So the C1 is connected to the 1. So count the C's first. There's 1, 2, 3, 4, 5. There are 6 carbons. And then this 1 means that this carbon is attached to that carbon. So it's going to give you cyclohexane, 6 carbons in a row. If you put a lowercase c, it's going to assume it's an aromatic carbon. And so this would be benzene of aromatic things. And you can get tricky by putting like a lowercase c in the middle of a straight alkane, and it will assume it's a radical and stuff. But this starts to get a little bit hazardous, that you might not get what you want. But smiles are very convenient. Once you get used to them, you can kind of read them and write them intuitively, just like another language. Yeah.
Branched molecules like
yep. Yep. How would he get branched molecules? You put the side branch in parentheses. I'll do an example in a second. So the adjacency list syntax. So RMG thinks internally as chemical graphs, where you've got atoms are represented by nodes and the bonds are represented by edges. And this is just a full description of the atoms. So we have to number them so that we can define the bonds. The only reason these numbers exist is so that the bond definitions make sense. You can reorder the numbers and it still remains the same molecule. Then we have the telling what the element is. So the element has to be something that RMG knows about. We then have 3 extra columns of atom properties. We have the number of unpaired electrons. This would represent radical sites. The number of pairs of electrons for like oxygen could have lone pairs, and some of the other species could have more. C is for a charge. Sometimes we have charge separation where you've got where you've got an atom with a positive charge and somewhere else in the molecule an atom with a negative charge. And then we have the list of the bonds. Now each bond tells you which atom it's bonded to and a property of the bond, like double, single, triple, benzene, van der Waals, etc. These have to be symmetric. So this atom 1 is connected with a double bond to atom 2. Your atom 2 line has to have a double bond to atom 1. Otherwise, it will say there's an error. You've got an invalid adjacency list. So that kind of checks that every bond you have to define both ends. So atom 1 is bonded to atom 3 with a single bond. Atom 3 is bonded to 1 with a single bond. So it kind of checks that you've got that right. A functional group. It's like a description of a molecule, but with wildcards and more flexibility. This is needed extensively throughout the database. If you're trying to do group additivity, you need to say, well, this represents a double bond to anything, or this represents a double or a triple bond. And so you need these wildcards and flexibility. So if you're editing the database, certainly the reaction templates or the functional groups, you'll need to understand these. But also, even if you never touch the database and you just deal with your own input files, they can be useful for forbidden structures, for example. You could say, I want to always block esters or whatever. You can write a functional group definition. So it looks very much like an adjacency list, but we've got the atom types here can be extended. So instead of just being an element like carbon, I can say R exclamation mark H, meaning anything except a hydrogen. So there's a few extra kind of definitions of group types here. We can also replace things with a list. So here I'm saying this could be a carbon with a double bond or an oxygen with a double bond. So automatically we see that there's element types that are not just carbon, but more specific types of carbon, and we can write lists. The multiplicity line here, I've got a list. You can also put a wildcard as an X. So you could say, here it says UX, meaning any number of unpaired electrons. So it's very flexible. I think you can describe almost anything. But you've got to think quite hard to do so. Some of these things, if you don't specify it, it assumes a wildcard and lets it do anything. And so you sometimes have to, you kind of quickly write a functional group and then you realize it's applying your reaction template to far too much and everything's going wrong. And then you realize, oh, I need to specify that there isn't a charge, or that it has to be neutral, or there must be 0 pairs or something. Otherwise, it assumes a wildcard. So sometimes you have to make it deliberately more constrained. Multiplicity describes the spin of the whole molecule. So you can say that there's a certain number of unpaired electrons on a specific atom, but also you might say the molecule as a whole is a triplet or a singlet or a doublet. So most radicals are a doublet multiplicity 2. Most ground shell species are multiplicity 1. Be careful, things like oxygen, the ground state is a triplet with 2 radicals and so on. If you don't specify the multiplicity, it tries to figure it out based on the number of unpaired electrons you've specified. But sometimes it's safest to be specific, and then you know what you're getting. Useful tools I will demonstrate. If we go to the RMG website, so the RMG website, molecule search is a great place to come to. Here you can type in a full adjacency list. So I can say I've got a hydrogen atom with 1 unpaired electron, 0 pairs, and 0 charge, possibly. Yeah. And I tell it to draw the molecule, and it draws my little H atom. And it also gives me other descriptions like the smile string. And here's the adjacency list. It's added the multiplicity. I can also enter things like caffeine. And if I hit tab, it will do a quick background search, find caffeine. This is my adjacency list for caffeine. And there's my picture of it. It tries to draw the lone pairs on the nitrogens and so on. And here's the adjacency list description. If you enter a smile string, it will, if you enter something that is a valid smile string, it assumes it's a smile string. So if I enter C, it assumes I mean methane and gives me methane. So this is a really useful website. your log file or your crash report or your RMG crashes and says this was the molecule, paste the adjacency list in here and hit draw molecule just to see what it is. Other useful buttons, generate resonance structures. If I was to do benzene and then I'll see 1, 2, 3, 4, 5. And then if I add some extra stuff on the side, someone asked about branches, I could do a molecule like this. If I say generate resonance structures, oh, I chose it badly. Let me pick something which actually has some. Stick some more double bonds in or something. Draw molecule. Oh, here you've got to hit tab, draw molecule. I might have chosen badly again. Yes, okay, I should have picked this. I had a demo example before. Caffeine again, will that have one? I don't know. Now I've spelt it wrong. I always get in trouble in lectures for making up demos instead of using my pre-prepared demos. Generate resonance structure. Yeah, okay. So there's a ton. Some of them get drawn with weird crossovers and stuff. This is a useful tool. These are all different molecules, but part of the same species. I don't think we've got time to describe all of that. Let me get back. Group draw is not working. There is sometimes when it's working. For another thing on the website in the other tools to draw functional group, if you're editing the database and you want to know what is this description, you can paste it in here and it will try to draw it, but it's not working. Surface adsorbates. In the adjacency list, use an X for the atom type. So we use X to represent any surface site because we don't know if it's going to be platinum or tin or ruthenium or what your catalyst is. Use X for your element in the adjacency list with 0 unpaired electrons, 0 pairs, and 0 charge. In the SMILES string, you can try inputting a star. So molecule search, if I do CC star, it's going to be ethane with an H removed, and so one of the hydrogens is replaced with an X. If a physisorbed species has an X but no, so this is ethane in the gas phase. If I was to add a 9th element, a 9th atom, which is X, but I don't bond it, so I've got the atom but no bonds to it, then it assumes that it's kind of van der Waals attached to the surface but with no chemical bond. And you could do that with a SMILE string by doing a .x, so cc.x. So there are shorthands you learn when entering things as a SMILE string, but I think that's the essentials. Yeah, the generate resonance structures is a useful button. Also, the searching thermochemistry, while we're here, I think there's another session on all of these features on the website, but it's there's some other useful buttons here. I think that's on time, but it was very fast, so there's probably some questions. Anyone have? Yes, questions.
So let me bring you Mike.
Oh, yeah, yeah.
So, did I understand it right that all these different species identifiers like SMILES, adjacency list, and so are equal? So I only need to use one of that, and then the RMG is transferring the others.
Yes, RMG can translate. So the quite yes. It's the adjacency list is most specific, and you definitely get what you asked for. The other ones, it's worth checking that you got what you expected to get. I was playing with other tools. I see on the whiteboard, I drew a little picture of a molecule, and then I photographed it, asked ChatGPT, what's the SMILE string for this? And it's amazingly quick and confident and completely wrong. And so then I asked Claude AI, and it was also confident and wrong differently. So these tools are very useful, but as always, check them carefully. When you're doing your own Python coding, the number one rule of debugging is see what's happening. See, like always be trying, am I seeing what I expect to see? There's some useful tools if in your Jupyter notebook. you can just say display M and it will render the picture. So I could do M dot, if I just say, what is M? That's the default in Jupyter. If I do string M, it will give me the molecule and it defaults to the smile string. I could do M dot to adjacency list. And if I do print M dot to adjacency list, it gets me the adjacency list. So these are worth exploring. Yeah, I could do something like this. Oh, backend. Oh, it gave me a warning, but it made a species anyway. And now I might be able to. Again, I'm live demoing something I've not tested. Generate resonance structures. Let's test it. See. Yeah, it made 2 resonance structures. Or yeah. Display I in. Okay. So yeah, you can do a lot, and it's worth kind of learning how to read these. You'll get used to it, but often the only way I can debug stuff is by really going carefully through the adjacency list and figuring out what's bonded to what. Is it what I expect?
I'll add to that. The smiles language is readily understood by like ChemDraw, Marvin, every piece of cheminformatics software. And if you know that you want to use some species, you can usually look it up on Wikipedia, and there will be a smile string in the information tab on the right.
I demonstrated, I picked on the AIs for failing today, but there's a ton of great tools that do get smiles right. And so, yeah, it's easy to find the smile for something. You Google it, and usually you get the right answer. I'm just a little warning, be careful of these LLMs.
Yeah. And just to reiterate too, the adjacency list will always render correctly because it says every single thing there is to know about the molecule. Smiles can be a little bit ambiguous, so double check your smiles.
If you're understanding how the adjacency list is working, it should be quite straightforward, or?
Yeah. But yeah, when reading a log file or something, it might say, oh, the problem was C or CC. And when it says the problem is C, you don't know, is that actually a carbon atom or is it methane? Like, is it showing me the species label or the species smiles? And if it was a label that it found in the database, it might represent carbon. And if it was a label it made up on its own, it probably represents methane. And so it's ambiguity when you're just skimming a log message. Always look at the adjacency list to say, what actually is this molecule?